Most applied problems that we're going to encounter that involve a normal distribution have a normal distribution that doesn't have a mean of 0 and a variance of 1. So how should we solve problems like this? So recall that a standard normal is a distribution that we're going to write with a density as follows: 1 over the square root of 2 pi e to the minus z squared all over 2. If a random variable is in a standard normal distribution, we know that it has a variance of 1 and an expectation of 0. So we are most likely going to encounter problems that are centered in a different spot. So if I use that for my variable z for the standard normal, let's say I use this variable x, it's going to be centered for the most part around some value we'll call mu. And instead of having a standard deviation of 1, they will generally have a standard deviation of some value sigma. And so we want some sort of density where if we take the expectation, we'll get mu, and if we take the variance of that random variable, we'll get sigma squared. So we're going to apply function transformations to the standard normal density. And by looking at the picture, there are going to be 3 things that we want to accomplish. First of all, we would like to apply a horizontal shift. So we would like to move the normal curve left-right. We're going to want to apply a horizontal stretch. The horizontal shift that we apply will allow us to center it at mu. Any horizontal stretch that we apply will allow us to get the correct, and I'll call it spread, of sigma. But then the final thing that we need to do is apply a vertical stretch, because a vertical stretch will ensure that after we not just move it, the moving won't change the area, but after we change the spread horizontally, we need to ensure that the total area is still equal to 1. So it turns out that we are going to define a new density related to the standard normal in the following way. We will apply a vertical stretch, we'll call it C, to the existing standard normal density. A horizontal shift, we'll call this A. We'll call B the horizontal stretch. And then we'll call C the vertical shift here. And the question that we're asking is, what A, B, and C will achieve the following? Now, another way to think of this, we could think of this as the standard normal density with these changes applied. And so there are 3 unknowns, and that means we're going to need 3 conditions. So the density condition, when we integrate this density over all possible values, we are going to need the result to give us a 1. So it's going to make our lives very easy if we treat this integration in terms of a standard normal. We're going to make a substitution. We'll say that z is x minus a over b. dz will be dx over b. Because the limits are infinite here, we are going to get the same limits. And so what will end up happening is we will get negative infinity, positive infinity, and we'll end up getting c times b phi of z dz. Now we know that this antiderivative, or sorry, this standard normal is a density. And we know that it equals 1, so therefore this integral exists. And as soon as the integral exists, we can start doing wonderful integral properties, like taking out constants. And so I can take this constant out, and I know that by definition of a standard normal, this is equal to 1, so I get a CB. So it turns out that I'll get B times C has to be equal to 1, so that means C will be 1 over B. Now, we'll also talk about the expectation. And what we'll need is that the expectation of our new density, we will want this to be equal to mu, because that's where we want the center of our bump to be. So as before, we will plug in what we've got. This time, I know that C is equal to B. And so my expression kind of looks like this. Once again, make the same substitution. Z is x minus a over b. This is just standard stuff from integration. dz will be dx over b. This time, the dx and the b will all connect. And note that if z is equal to x minus a over b, then x is going to be a plus b times z. So if I substitute all of this stuff inside, I'll get a plus bz, 5z dz. And because I know that all of the integrals I'm going to encounter exist, because I already evaluated them from the standard normal, I'm going to just jump ahead and show you what we end up with here. So it's going to turn out that we end up with the following. This is equal to 1 by the definition of a density, the standard normal density. And this is equal to 0 because this is the expectation of the standard normal. So at the end of the day, all we're left with is a. And this determines one of the constants. Because we want the expectation of this new normal to be mu, we've determined that a is equal to mu. And so the final thing that we need to talk about is the variance. And so the variance of x is going to be calculated as follows. From this result above, we'll get e of x squared minus mu squared. And then we're going to continue playing the same games we played up to now. We will take the definition of expectation of x squared, and we'll substitute in our result for the density. And now we'll have x minus mu over b. We're slowly filling in the gaps. But the process is always the same. Write everything in terms of the standard normal density and work with the results that we know from there. As before, a lot of things will simplify. And we will get the following details. We'll get negative infinity to positive infinity, mu plus bz squared, phi of z dz minus mu squared. If we do a little bit of algebra and FOIL this out and spread everything out, we will end up with the following. Z squared phi of z dz plus 2 mu b z phi of z dz plus mu Oh, sorry, my mistake here. This should be just a mu squared times phi of z. And over on this last result, we'll get b squared z squared phi of z dz. And we'll have a subtraction of a mu squared. A lot of the results from before will apply. This is 1 because it's the density. This will be 0 because of the expected value of the standard normal. And if we look back at the variance of a standard normal, this result will give us a 1. So what we end up with is a mu squared plus b squared minus mu squared. And so we just end up with a b squared. Now, it's a lot of details here, and I wanted to show them to you because there's power in understanding this transformation idea. And so, we want the variance to be sigma squared, and so this implies that b will be sigma because we always want a positive value there for our b. And so we have found the 3 terms. So this is what we are going to call a general normal density. If we've got a function that is now in this form, 1 over sigma x minus mu over sigma, this will be the general normal density. This curve will correspond to some normal bump centered at mu with a standard deviation of sigma. If our random variable is said to be normally distributed with mean of mu and variance of sigma squared, and note that this entry is always variance and not standard deviation, we have just proven from above that this result will give us the desired mean and the desired density. And now that we've got this in place, what we need to do is to be able to understand how we can use this to calculate areas.